Hello, everyone. So we're going to do 4.3 exponential equations and functions. I'm hoping to make this video shorter than last time because I know last time was a little bit long, but we had a lot to go through. So an exponential equation is an equation that has an exponent containing a variable. Solving exponent equations, well, we have some strategies to look at. We begin with, we want to make sure that we can rewrite the original equation in the shortest form possible. Then we also want to look at having the same base. And then we're able to either set the exponents equal to each other or use our inverse with logarithms to help us solve. But more than likely with this section, we are changing the bases enough to be able to solve, okay? So first we have example 1, solve the equation. We have 2 to the x squared plus 5x equals 116. So right now what I want to think about is having the same base. Well, if you think about this, 2 to the x squared plus 5x stays the same, and 16 is 2 to the 4th. But because it's a fraction, we have to remember a fraction makes a negative exponent. This is very important. I see a lot of kids overlook that. Now that our bases are the same, we can focus on the exponent, which is x squared plus 5x equals negative 4. Now we have an x squared, so we have to think about factoring. So let's move everything over. We have x squared plus 5x plus 4 equals 0. And then we factor, so we get x plus 4 times x plus 5 plus 1. So x equals negative 4 and x equals negative 1. Plug back in to see if it works. We can do that in our calculator. When you do that, both of them do work. Example 2, we have a little bit of a difference here because we have this 2 and the 10. The 2 and the 10 are being multiplied. So of course, the first thing we can do is to divide both sides by 2. When we do that on the left side, we get 5 to the 3x minus 1 equals 5 times 25 to the x. Now, this is where I want you to be very careful. Remember that in order of operations, we have to deal with the exponent first before we divide, or multiply. So do not multiply the 5 and the 25, okay? First of all, our left side stays the same. We have 5 and 25, so this is 5 to the first, and 25 is 5 squared. We already have an x there. Okay, so does everyone see how that looks? Now, when we have the same base, again, we do not want to multiply those. When we have the same base and it's multiplication, what do we do to the exponent? We add the exponent. So this is actually 5 to the 2x plus 1. Multiplication means we add the exponent. We don't multiply the bases. This is very, very important. Now that our bases are the same, we can set our equation, our exponents equal to each other and solve. Plus 1. So we get x equals 2. You can plug back in to make sure that works, and it does. All right, solve the equation. All right, first thing I want to do, because I want to make sure that our bases are the same and everything, is actually move this constant over. So we're going to have 5 times 10 to the negative 2x equals 73. And I want to get rid of that 5. It's multiplying, so we're going to divide both sides by 5. And yes, we get a fraction. But guess what? Who cares? They exist. We need to get used to them. Now, in this case, we can't get our bases to be the same. And what did I say at the beginning of this lesson? We're either going to get the bases the same so we can look at the exponent, or we're going to have to use our inverses. Well, if we have a base 10 here, that means we have to do log base 10 to get rid of it. And whatever we do to one side, we do the other. Okay, and those cancel. So I get negative 2x equals log base 10, or you can just say log 73 over 5. Now I'm going to do the exact, and I put 75. I'm going to do the exact value, so I'm not even going to put that in my calculator right now. And then how do you get x by itself? We divide by negative 2. So I have log of 73 fifths all over negative 2, and I'm done. Now, in your homework, they might have you do the approximation that you can just do in your calculator and give that decimal out. Here's another one that's tricky. Remember, lately I've been saying whenever there's tricks, you need to make sure you understand them because they're probably going to be on your test. Okay? Well, e to the 2x, 3ex minus 10. Well, what does this look like, guys? This looks like x squared plus 3x minus 10. And I want you to think of it like that. But instead of x's, usually when people do this, they use u. They use what's called u substitution. In other words, we're setting u equal to e to the x. So that's why we would get u squared plus 3u minus 10. Now I'm going to factor. You get u, this would be plus 5, u minus 2 equals 0. Now, of course, we would set each part equal to 0. Here is where most people make their mistake. Did we begin our equations with u? No, we did not. We used them with e's. So I have to substitute the e to the x back in before I solve. Okay, so now I get e to the x equals negative 5. And on this side, I get e to the x equals 2. Well, how do we get rid of e to the x? ln, both sides. So I'm going to write this out, but I'm hoping you're coming up with the conclusion here. We get x equals ln to the negative 5. And I'm hoping right now you're getting like this. No, 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 it can't be negative. Remember, in ln's and log, you can't be negative and it can't be 0. So we can cross that answer out. But on this one, we have x equals ln 2. And there is our answer. All right, finding the intercepts is often important when graphing. All right, so when finding the x-intercepts of the graph, what we need to do, remember, is we were solving by making the whole equation equal 0, right? X-intercepts are when f of x or y equals 0. So just set it equal to 0 and solve. So 2 to the x squared minus 5 equals 16. Well, we can change the bases. Recognize that 16 is 2 to the 4th. This time we don't need to make it negative because it wasn't a fraction. Same basis means we can focus on the exponent. So x squared minus 5 equals 4. And solve. X squared equals 9. Be careful, many of you guys forget this. When we take the square root, how many answers do we get? We get 2 plus or minus 3. So our x-intercepts are 3, 0, and -3, 0. This is the other part that people make a mistake on. X-intercepts are coordinate pairs, so you need to make them coordinate pairs. All right. One more? Couple more. Let's do some graphing, okay? Graphing exponential. So a couple things. Find the domain. Recall that y equals b to the x. It's defined for all x values. We need to find the x and y intercepts. We have to talk about transformations. Plotting points if we need to make sure things are correct. Think about the horizontal asymptote, because remember in a exponent, usually we start out with our asymptote being at 0. And then we're going to sketch our curve, okay? So let's think of this. The domain. Well, remember the domain for an exponential is -infinity to infinity. To find the x-intercepts, we set our equation there. 3 2x plus 1 minus 1 equals 0. So then we solve. Okay. Now think of this. This is the tricky part here. You're like, wait a second, we can't get the bases to be the same, but we can, because 3 to the 2x plus 1 stays the same, but 3 to the what would equal 1? 3 to the 0. That was a trick right there. So set the exponents equal. All right, we get x equals -1/2. So remember, that's a coordinate pair, so -1/2, comma 0. Okay. Now we want the y-intercept. Okay, y-intercept is when x is 0, so let's plug in 0 there. We get 3 to the 2 times 0 plus 1 minus 1. So 3 to the first minus 1. So what do we get? 2. So our y-intercept's at 0, 2. All right, let's think about transformations here, because that will help us with our asymptote, okay? First of all, the -1 at the very end makes it go down 1, which makes our horizontal asymptote y equals -1. All right, then we have this 2x plus 1. So the plus 1 on the inside makes it go left 1. And the 2, of course, makes it do that vertical, or in that case, does a horizontal stretch or shrink. But really, we don't have to worry about that right now. We can look at these other points and just connect. So we have, get the horizontal asymptote right there. And we get the -1/2, 0. It's our x-intercept. And our y-intercept is 0, 2. And then because we have our 2 points, all we have to do is connect. Okay. Now, if you needed to be 3 or more points, you guys, all you have to do is plug in a value and estimate where it is. All right, let's see, one more graph. One more and then an application. Okay, so on this one, let's talk about domain. Domain, of course, exponential, it's -infinity to infinity. X-intercept. Let's set this equal to 0. We're running into the same case, right? Well, no, we're not. We have to actually log, right? Because we can't do the same bases. So to get rid of 10 is we log both sides, right? But what happened, guys? Uh-oh, we can't have log of 0. So that means, so let me make this note. Log of 0 does not exist. Just to remind yourself in your notes. So there are no x-intercepts. Okay. y-intercept, plug in 0 for x, so 10, the 1 minus 0 squared, of course, is 10, so 0, 10. All right, now this one's going to be a little awkward, right? Because it's kind of hard to see, especially since we're squaring x right here. We can't really talk about transformations when we have an x squared in the exponent. So the best thing to do now is just to use points, okay? What I also want to tell you is it did not go up or down. So that means the horizontal asymptote is still at y equals 0. So let me at least plug that in. And I'm going to plug in or at least show our y-intercept. Now remember, it's supposed to be exponential, so we should have a curve, but which way does it go? And we have to make sure for both ways, okay? So if you plug in -2, you get this crazy decimal that when you put it into a fraction, we get really, really close to 0 there, right? And if we plug in -1, you actually get the value of 1. If you plug in 1, we get the value of 1. If we plug in 2, we get that small decimal again. So again, when in doubt, when you can't use transformations, plug in points. So if we see at -1 it's 1 and at 1 -1. Now remember, it curves. So what happens, guys, is that it actually will have some symmetry there. And the reason why it has that symmetry is because of the x squared. Isn't that crazy? One more and then we're done. Okay. Here we go. Suppose a new car loses a fixed proportion of value every year. Its value after t years is v of t equals v subset 0, 1 minus r to the t, where v subset 0 is the initial value, that's very important, and r is the proportion of yearly loss. Excuse me. If the car was bought initially for $25,000 and loses 20% every year, how many years will it be worth $10,000? Okay, so let's think about what we're talking about. That means v subset 0 is 25,000. And r, now don't forget to put your r as a decimal, so that's 0.2. So when I look at the equation right now, I have 25,000, 1 minus 0.2 to the t. And what I have here is I have the value. So t stays the variable because that's what we're looking for, how many years. So the value is the v of t. So we put the 10,000 right here. Now I'm going to set this up going little by little here. So first, of course, what I'm going to do is 1 minus 0.2, which is 0.8 to the t. Why didn't I put 2? Okay, now the next point. I'm going to mention this again. I've mentioned it earlier in this lesson so far. Do not multiply that. You cannot multiply different bases. So in other words, if I can't multiply it, I have to divide both sides by that 25,000. When you do that on your calculator, you're left with 0.8t equals 0.4. Now, from here, we have to get rid of the 0.4. Okay, I know you might think, oh, let me do some nice tricky stuff with common bases. Don't do it. One of the things I want you to remember is any time that you are working with time and growth, you're going to use the natural log, okay, ln. So to get t, because that's the idea, is to get t by itself. We need to get it out of the exponent, so we're going to ln both sides. Well, what does that do? That doesn't get rid of the 0.8, but what we can do now is bring the exponent in front. So we have t ln of 0.8 equals ln of 0.4. So we're going to divide each side. So we get ln 0.4 divided by ln 0.8. And because it wants how many years, we're actually going to approximate this out. So 4.106 years. And we're all done.